Good morning, everyone. My name is Juan Jose, as Santiago said, and I'm going to talk about a study I did together with Juan Fernando Salazar, Juan Camilo Villegas, and Angela Rendon. The title of my presentation is Forest-Induced Temperature Inversions Reveal a Regulatory Mechanism for Surface Water in the Amazon. First of all, I wanted to mention or highlight that the fluxes of matter and energy from the surface to the atmosphere are highly relevant in the Amazon because they play an important role on regional and global scale dynamics and especially on the hydrological cycle. So the amount of evapotranspiration from the Amazon is estimated to be in the order of about 8 trillion tons of water per year. And there is also an important aspect which is called precipitation recycling that is about 25 to 50% of rainfall in the area. This is like 50 up to 50% of the precipitation that falls in the Amazon has been previously evapotranspirated in the basin. So the characteristics or the partitioning of evapotranspiration into transpiration and evaporation depends on the amount and the characteristics of vegetation. So this is important because of biological conditions, yes, how much of the total evapotranspiration has been transpirated, so it's biological flux, and how much of it is direct evaporation, which is abiotical flux. So, for example, if we have a very dense vegetation area, we estimate to have less direct evaporation from the soil or intercepted. And if we have a more sparse vegetation, more sparse forest, we have much more part of the evapotranspiration that is direct evaporation. The factors that influence how much water is directly evaporated from the soil depends on several factors associated to the forest. Some is the available energy that is at the soil because, of course, in forests, a lot of the energy is absorbed in the upper part, so you have like a special shadow on the forest floor. Also, because of the roughness of forest, you have reduced wind speed that is also important for evaporation. And litter production because it creates like a layer of leaves that restrict evaporation, among other factors. There has been a new or a relatively new factor associated to temperature inversions. Some Russian authors that have been mentioned before on this day said that the formation of a temperature inversion in the forest, that is the temperature increase with height in the forest below the canopy, creates conditions that restrict vertical transport processes of moisture. And if you restrict the direct vertical transport process of moisture, you have more moisture on the surface available for transpiration. So this has been discussed from a very theoretical point of view, and what we wanted to check if this is seen in observations and if there is occurrence of temperature inversions actually in the forest. If these inversions occur, are they associated to the vertical distribution of moisture as suggested? And also we wanted to check the seasonality of this phenomena because we know that some areas in the Amazon have very long dry seasons. And if you have a mechanism that restricts the loss or the direct loss of evaporation from the soil is important, especially in that season when you have less amounts of water. And finally, just to discuss a little implication or potential implications of the loss of forest and the associated loss of this mechanism. So a little bit about the data that we used to check this mechanism. We had information from a eddy flux tower it belongs to the LBA project. It's a huge project around the world. And what we have there is measurements of temperature on 8 different levels from about 0.6 to 60 meters, and also from water vapor. about 7 levels from 0.9 to 60 something meters on a temporal resolution of 1 hour. The seasonal analysis, the division into the different seasons, we did from the rainy season from January to June and the dry season from July to December. And after cleaning and eliminating all the data with problems and gaps, we ended up having about 208 days per each type of season. So several dry seasons and several rainy seasons. And as we are interested in the fluxes of water vapor and energy, we restrict our analysis to the daytime. So from 6 in the morning to 6 in the afternoon. First, we had to detect if we had an actual temperature inversion or not. So what we developed is an algorithm that checks on what type of temperature profile we have. This we had to do because the real observations are very noisy. So you have small decreases and then increases. But at the end, if you check the entire profile, you see it's highly uniform. So we divided all of the profiles into 3 different categories. The first and most important for us is surface temperature inversion and temperature increases with height. Another type of profile is where temperature increases with height, but above a certain level. And the rest is just no inversion. It can be a very uniform or a decrease of temperature with height. All the analysis from now on is going to be divided into these 3 categories. So what we found is that during the day, there is actually a lot of temperature inversions in the area. This is what we see in this first panel. In this first panel, we see that the number of temperature inversion of surface-based temperature inversion is much higher than the other profiles. We have about 1,700 profiles with this inversion, about 600 profiles with elevated inversion, and only about 200 profiles where there is no a clear temperature inversion. All the profiles here are normalized, so they start in 0. This is done just by subtracting to every level the level at the first, the value at the first level. And what we see, what we wanted to see after checking that we have a lot of inversion is whether this inversion actually has an effect on the vertical distribution of humidity. And that's what we can see on the panels of the bottom. And what we see is a very different behavior when we have a temperature inversion than for the other 2 categories. When we have a surface-based temperature inversion, we have a moisture profile where most of the values or the highest values are found close to the surface. If we have like higher values of moisture close to the surface, we have conditions closer to saturation, and then we limit, or we can say we limit direct evaporation. As I said before, we wanted to check the seasonality of this mechanism, so we divided the analysis in the rainy and in the dry season. And what we can see is that we have a higher occurrence of temperature inversions in the dry season. About 60 of all the analyzed profiles of surface inversion occur in the dry season. Another important fact is that temperature inversions do not only modify the vertical structure of moisture, but also we have higher amounts below the canopy. The green stripes that you see is the canopy. This is the canopy. And what we see is that when we have an inversion, which is the solid thick line, we have higher values of water vapor. One other thing that we wanted to study is the duration of the temperature inversion in each season. So it's good if we have a higher frequency of inversions during the dry season, but we wanted to know if the actual inversion is more persistent, it lasts longer in the dry season, or is more sparse, that the net effect might not be the same. So what we find in these histograms, what we have in the bottom panels is the maximum duration of the temperature inversion per day in this period that we analyze, 6 to 6. And we can see that during the dry season, what we see is the inversion is more persistent. It tends to be 6, 7, 8 hours per day, while in the rainy season, it's only 1 to 2 and 3 hours. So the inversion is occurs more frequently in the dry season, and it's longer. It lasts longer in the dry season. So the effect of the mechanism is more effective, I would say. Finally, we checked if there was we checked a correlation test about the gradient of moisture and the gradient of temperature. And what we see is an inverse relationship between the two gradients. So when we have a positive temperature gradient, we have a negative moisture gradient. So if we have a temperature profile that increases with height, we have a moisture profile that decreases with height. The higher amounts are close to the surface. In summary, so what we wanted to check and what we think we are seeing in the observation is that we have some deformation of surface-based temperature inversion that depend on the vertical structure of the forest, because the higher heating in the upper part is associated to the absorption of radiation in the leaves, and this temperature inversion limits the vertical transport and limits evaporation, direct evaporation from the soil. And by limiting the direct losses of evaporation, we have more available water in the soil for the forest for transpiration. So at the end, it benefits the forest itself. As a discussion, we believe it's very important that we find a higher occurrence in the dry season. This is no surprise, as the mechanism depends on radiation, and we have higher amounts of available radiation in the dry season, less clouds. And because also, if we have a mechanism that restricts the losses from the soil, is important in the dry season when we have less inputs via precipitation. Also, it's important for us, as if we don't have the forest, if we lost the forest, we lost this mechanism along with the other mechanism associated to forest, and then it might amplify the dry conditions during the dry season. And also it nourishes the debate about the potential impacts of deforestation in other aspects, yeah? So as a conclusion, what we found is that the formation of temperature inversion is very common phenomena in the Amazon. We find that it is actually closely related to a distribution of moisture that limits direct evaporation. And we found that there is a higher frequency of occurrence and a more persistent or longer persistence of the mechanism in this season. That this mechanism depends on the vertical structure of the forest. If we don't have the forest, we lose this mechanism. And also that it's a potential control or a potential regulatory mechanism on surface water in the region. Thank you.